In the last tutorial we did our first simulation. Now we're going to do the analysis or the post-processing on it in the IPython notebook. To analyze the simulations, you're going to need to install the IPython notebook and the Python pandas library. Optionally, you can also install my library scikit-spectra, which will add a couple bells and whistles like 3D spectral plots. But in this case, we're only going to use pandas. To begin, I'm using Pylab inline to do all my plotting in the notebook, inline in the notebook. And the object we're going to use to analyze the simulation is called the layer sim parser. So we import that from PAME sim parser, and we're going to instantiate it by doing layer sim parser .load pickle, and we pass it the path to the simulation pickle file that we just saved, filfrac.mpickle. That's going to return a parser object that's going to make it easier to go through all of the data that was stored from the simulation. By the way, if you come to PAME's home folder and you go to simulations and you go to sim tutorial, there's an IPython notebook tutorial that gets into much more detail about how to parse these simulations. Notice that there is the parser.summary method that breaks the results into four types: inputs, like the volume fraction; primary results, about, which has metadata about the simulation; static parameters, which would include the x values, the fiber parameters, and other variables that can't be simulated over. We're going to go through these for our simulation as follows. For some reason, parser.summary is giving me an error, some bug that I haven't fleshed out. So that would just give us this kind of information, this summary. Parser.about shows the notes that we took for our simulation. Remember, we wrote this. It also shows the parameters that we chose for storage. Recall that I only stored the reflectance, the transmittance, and the absorbance, and I only stored the averaged angles. I didn't store these values for every angle or every mode in the fiber. Info is not a valid keyword. Yeah, I meant inputs, obviously. And this just shows you that the only simulation variable was selected material.volume fraction. To look at the primary results, we can do parser.primary. Remember when we were doing the simulation, I picked the results that I thought would be most important, these quantities? Well, here they're stored in an ordered dictionary. So for each step 0, the value of R average, reflectance, T average, transmittance, and A average is stored. And this is all of these results are stored in these nested JSON structures. However, for the primary results, we can use a primary panel, which is a pandas object. This is a structured object that makes it much easier to parse and plot the data. It gives us the full power of the pandas library. Along the items axis, we have A average, R average, and T average. The major axis is our wavelengths, and the minor axis are our increments. Let's create a parser panel, a primary panel, but let's pass a keyword that instead of a minor axis being labeled step 0 through 9, we'll label it with the values of the volume fraction. In other words, we tell the primary panel, use these values. This will be nice for plotting. And let's give it the prefix VF underscore. In doing so, that returns a primary panel that has minor axis values VF0 to VF0.2. And that's pretty much just a cosmetic change, so you could have worked with this primary panel if you preferred. if I do results.items, now results is now a pandas panel. So keep that in mind. All these methods are now the pandas library API. So results.items tells me that, as we saw before, the index is A, R, and T. We could slice the results for the R average, and that's going to give us a data frame. If you're not familiar with pandas, it's like an Excel table where on the rows we have the wavelengths, and along the columns we have the volume fractions that we incremented over in the simulation, and in the data we have the corresponding values of the reflectance, or the average reflectance. We can do a similar thing for T average and A average, and I'm going to write these into variables R, T, and A for easier access. Okay, now it's time to plot the reflectance. Since the reflectance is this table, and it's a pandas data frame, we can just call r.plot. And let's pass a color map seismic, which is going to go from blue to red with increasing volume fraction. Now we can see the reflectance as a function of volume fraction over the course of the simulation. This data is much more clear than trying to do this interactively through PAME's user interface. It might be hard to tell, but the data started at this flat line, it initially dropped, and then it rose again, and this is the inversion that I spoke of before. The jaggedness of this peak is because I'm using the Johnson and Christie data set for gold. If I had used the preferred data set from part 2, simulation, or tutorial 2, this would be smoother. Let's focus on the first 6 curves so we could see this turnaround nature a little better. We can use the pandas API function ilog to specify that we want to keep all the wavelengths, but we only want the first 6 curves. And again, we just plot that. Now you can see the nature of the turnaround a little more clearly. By the time the fiber coverage got to 0.06 fill fraction, the inversion was already in progress. Instead of just the reflectance, let's look at the reflectance, the transmittance, and the absorbance. Similarly, we could do this for any parameter that we had specified to save during the storage, so we can look at a lot more than just these. I'm using matplotlib to make a 1:3 multiplot, and the reason that the line widths are set this way is because I have a default matplotlib config that might look a little different if you don't have the same config file. Now we can kind of look at these as a pair. The reflectance drops and then rises, and I'm going to characterize this as a relative inflection. The transmittance, on the other hand, does not inflect, and the absorbance, which is being absorbed in the layer, also does not inflect. Finally, I'm going to normalize this data. What does that mean? Well, the reflectance had an initial value at 0.002. This is pretty much a flat line, but it's a baseline, and under certain circumstances, this baseline can have some dispersion. So it's smarter to divide all of these curves by the first curve. So we say r.divide r of step 0, and this is just the command to divide along the correct axis. This is again just the pandas API. So if I normalize all these to the very first curve, oops, it's not called step 0, it's called VF0. That's what that prefix did. What is it called? R.keys. This is when you gotta kind of know the pandas API a little bit. but because I changed these keys initially, I have to make sure I pass the right ones. And now you can see the normalized values. The reflectance is normalized to 1, as is the transmittance. This doesn't change the overall profile too much, but it does bring out some interesting points. And also the absorbance, we don't want to really normalize it because it's already a normalized quantity. It defaults to 0, so we get these infinities, or this noise enhancement. But here's the peculiar thing that I'd like you to take away. The reflectance drops all the way to 0. In the lab, I've built this fiber, and I've done this self-assembly process and monitored the normalized reflectance in real time, and it looks exactly like this. The only difference is my data never gets to 0. It only gets to about 0.2 before the inversion takes place. We theorized that this could be due to the intermediate film between the glass and the gold particles, and in the last tutorial I'm going to show you that indeed that is the case.